only mode.
Good morning. My name is Tim Ballinger. I'm with Bruker Nano Inc. and I want to thank everyone for joining us this morning for the presentation on ISO versus ASME, the basics of surface profile filtering. This is part of Bruker's webinar series, and if you would like to get more information on some of the future webinars or some of the past webinars, you can go to the Bruker website and find out more information. Wanted to just give you a little information up front. There will be time at the end for questions, and if you have questions, please just type them into the little box that you see that says question. And you can type those in, and then we will be able to answer those at the end. Right now, everyone's telephone and microphones are muted so that there won't be a lot of background noise during the presentation. So once again, thank you, everyone, for joining us. I also want to encourage everyone to participate in a survey at the conclusion of the webinar. That helps us get information about what you find valuable in these webinars so that we can make the most effective webinars in the future. So please participate in the survey at the end. It helps us make better webinars for you for the future. So with that, I will begin the presentation. And again, once again, thank you, everyone, for joining us today. Just briefly, I'm going to give an overview of the presentation that we're going to talk about today. I'm going to start with a history of both the ISO and the ASME organizations and the standards that they provide for the world. I'm also going to talk about the ISO versus ASME, what's the difference, the contrast and comparison of the two different organizations and the standards that they provide. I'm going to talk a little bit about stylus profiling. That's going to be the main focus of this presentation. And off to the right, you see a picture of a diamond tip stylus on a textured surface, a machine part. And so we're going to talk about how filtering is done with stylus profiler measurements to get the most usable and accurate measurements for your process control. We're going to talk about how to glean roughness and waviness data from the raw stylus profiler data so that you get the information that you need for your optimize your process. We're also going to talk about some of the improvements in the software over the years. Stylus profiler has been used for over 50 years for looking at surface texture, and recently there's been a lot of improvements in the software and the ease of use of these systems to make them even more valuable for surface texture type applications. We're also going to talk about some of the practical applications of stylus profilers and surface texture, and even how things like the stylus size and shape and noise and other things can affect the stylus profiler measurements and act as filters of the data, in fact. And so at the end, I'm going to provide some references that you can also check out to get more information on what was presented here today. So with that, I'm going to give you just a brief history of first ASME, then the ISO. So ASME was founded in the 1800s. So 1880, they were a group of engineers that got together to discuss concerns that typical engineers have by the rise of the Industrial Revolution in the United States. But something happened in 1905 that really changed everything. So there was a huge boiler explosion at the Grover Shoe Factory in Brockton, Massachusetts. And it killed 58 people and injured over 150 people. It's a terrible disaster. And this was the result of a boiler that had exploded. And a few years earlier, in 1884, ASME had developed a code for boiler testing. And this kind of became a huge event due to this disaster that happened. So people started realizing that there are some things that can be done to avoid disasters like this in the future. So ASME actually formed a boiler code committee in 1911, and that code was incorporated into the laws of the United States as well as Canada and throughout the world, in fact. And so ASME really became came to the forefront of this type of industrial technology of machining and wear and friction and things like that, and how to control these things. So this disaster actually served to help future disasters from happening because of the light that it brought to testing and surface texture and how to control quality of certain types of components such as these boilers. As far as ISO is concerned, ISO was also started in the United States in 1926. It was originally called ISA, not ISO, which was the acronym for the International Federation of National Standardization Association. However, their primary focus was on mechanical engineering. But in 1942, it was disbanded during the Second World War. I guess all the engineers were working on bombs and aircraft and things like that, and for some reason, everyone was needed to help in the war effort. But in 1946, 25 delegates came together from different countries, really gave it an international flair, and they all met in London at the Institute of Civil Engineers and created a new organization which was created, in quotation, to facilitate the international coordination and unification of industrial standards. So ASME originally came along and was more of a focus on the United States and Canada, and they started being adopted internationally. But people really realized that there needed to be more international standardization, not just in the United States, because even though the United States had standards, every country had different standards. So ISO came along and started putting emphasis on we need to have standardization across the globe. So even the name of the organization, it's not an acronym. A lot of people think it's an acronym for the International Organization of Standardization, but if you translate that into different languages, that acronym doesn't make sense. So the name ISO actually came from the Greek word isos, meaning equal. And the reason why that's important is how it relates to standards. If two objects meet the same standard, they should be equal. So ISO was created to create equal standards throughout the world. So, what's the difference between ISO and ASME today? Well, if we look at the automotive market, for example, the European automakers typically apply ISO standards, and the U.S. automakers apply ASME standards. Now, that isn't strictly across the globe the way it is. I mean, that's just kind of a generic, because if you look at Western European countries like Germany, France, and Italy, of course, they predominantly go with the ISO standards. However, there are Eastern European countries such as Poland, Hungary, and Romania that adopted ASME standards because they provide them access to the U.S. market. So, there is still a debate going on as to what is the best or what should be used, the ISO versus ASME. And that is really, I think, something that each organization and each company needs to determine what is best for them, what is best for their company, for their sales, for their organization. You can't come to me and ask me, well, what should we use, ISO or ASME? I think the real answer to that question is you need to pick the standards that work best for your organization, for your parts, for your company, and stick with it. Because, of course, anytime you change any parameters, your measurement's going to change. So you just need to stick with a parameter and make sure that that becomes standardized throughout your organization. And you typically pick a standard that maybe a supplier of yours or a company that you supply uses. So that's how these standards typically work. So how do the ISO and ASME standards apply to Stylus profilers and the filtering thereof? Well, Stylus profiler is kind of a crude drawing of Stylus profiler on the left, scanning across the surface of what we call a real profile, the actual surface of a part. And so the Stylus profiler collects the data by scanning across the surface. Some Stylus profilers scan the stylus, move the stylus across the surface. Other Stylus profilers move the sample below a stationary stylus. doesn't really matter which method is used. The bottom line is the Stylus profiler just moves up and down as it scans across the surface and collects the data of the sample surface. So the Stylus profiler collects the data and displays it on the surface of what we call the total profile, which is the unfiltered or the raw data that is collected from the Stylus profiler. Now, we typically almost always apply some filter to the data, what we call the primary profile, which is typically a short cutoff filter which is applied to remove noise in the data. So you don't typically look at just the raw data. You're almost always looking at some sort of filtered data. Now, the primary profile in this example, you see here a shape that's got some curvature to it. It's got some high-frequency roughness on there and kind of a lower-frequency waviness. So all of those components are exhibited in the primary profile. The goal in filtering is to try to separate those values. So here we look at, there's a red line going across the bottom, which is the roughness data, which has been filtered to remove the shape and the waviness of the data and only look at the high-frequency roughness signal. Then there's kind of a waviness signal that's kind of interspersed in between the primary data that looks at the low-frequency waviness of the surface. So, and you could even do a further filtering of the data to look at the overall shape of the surface. So sometimes you want to look at curvature as opposed to of just the waviness of the surface. So you can apply a multitude of filters to the data to collect the data and organize it in the way that's most appropriate for your application. So looking at the roughness profile, the way we generate the data is by applying the filter. And typically we use the sampling length, which is equal to the filter cutoff wavelength. So basically, the spatial frequency is less than the cutoff wavelength, and the resulting is what we call the roughness profile. So here we remove the overall shape, the waviness, and you can filter this even further with a shorter cutoff to remove even more waviness from the data if you so choose to do that. The waviness profile is taken from the same data and using the same cutoff filter, but the data that is passed through, or the data that's greater than the cutoff wavelength, is what we call the waviness profile. So it uses the same cutoff typically for the roughness and the waviness. It's just that one passes through the data and the other one filters the data. So that's the difference between the waviness and the roughness profile. And again, we can filter the data even further by using a longer wavelength to create what we call the shape profile. So, so all this data can be displayed and filtered to give the information that you need for your particular process. So if you're interested in shape, if you're interested in the waviness of the profile, or the high-frequency roughness, all that can be collected from the same data set. You don't need to do multiple scans to collect the data. So a little bit more information for those of you who are interested. People just kind of giving some definitions that are used when we're talking about filtering. Often you hear the term traversing length. And traversing length is just the distance of the total scan that is collected by the Stylus profiler. The evaluation length is the selected portion of that overall traverse length. So typically the evaluation length is shorter than the traverse length, although it could be the entire length. And so you're just looking at a selected portion of the overall data. And then within the evaluation length is what we call the sampling length. The sampling length is typically less than or equal to the evaluation length. And from the sampling length is what we derive the roughness and waviness profiles from. So the sampling length is typically equal to the cutoff length for lambda over C. Going a little bit deeper into this discussion of the sampling length. So the sampling length is typically made up of multiple segments of the profile or the evaluation length. So the segments of the profile showing the distance between the peaks and adjacent values. So We also identify some additional peaks in here with the sampling. And so this is based on the ISO 4288 standard. So this information is typically collected from the data to give you the filter that you require for a specific application. So with that, I'm going to talk a little bit more about how we determine ISO versus ASME. So I took an example here of just R sub A, or average roughness. So both ISO and ASME have calculations for determining the average roughness of a profile, although they use a slightly different calculation to achieve the same goal, which is to get an average of the surface roughness. Now the ISO standards, the 4287 and 4288, typically look at the R sub A, but also look at the roughness over the sampling length, which is represented in N. So N is a number of sampling lengths across the evaluation length of the profile. ASME uses a specification B46.1. Some people remember ASME also is referred to as the ANSI specification, but the ASME is the standard of B46.1. And so RA is calculated where N is a number of data points of the roughness profile over an evaluation length, and Z is the height of the value of the roughness profile. So both of these, ISO and ASME, provide very accurate calculations of filtering for roughness for many different applications. Again, it's just the individual company or organization needs to determine which is most appropriate for their particular application and for their customers. So again, you need to really determine what works best for your organization and stick with that and try to understand the differences between the ISO and the ASME standards. So I'm going to give examples here of how to do filtering. And this is data that was taken on a Bruker Dektak XT Stylus profiler. The Dektak XT is a Stylus profiler that was introduced last year. And it's used for a variety of different applications, surface roughness as well as step height measurements. So we're going to talk about how, using this example, how to go through and appropriately filter data to get the information that you need. So displayed on the screen here is the raw unleveled data, or the total profile. So you see there's maybe some slope in the data, and this could be there's some tilt in the sample. And in order to get accurate measurements, the first thing you need to do is remove that tilt or that out of levelness of the surface, in addition to do filtering. Now the Dektak XT has a very easy-to-use software, and it's got big buttons off to the right here, you see, to enable you to do things like roughness measurements or data leveling. So with the Dektak XT, you select the data leveling button, and the data leveling settings is displayed. So when leveling, you need to determine what is the best or most appropriate leveling. So you can either do two-point leveling using cursors at two ends of the profile, and so it will level the data based on those cursor intercepts and make both those cursor intercepts 0. Typically, people will just use a linear fit, where it just takes all the data points across either the entire total profile or the evaluation length, and gives you an average of all the data points and levels it based on that. You can also do things in like curvature removal, and so there's a lot of specific things that you can apply to the data to achieve the leveling that is best for your particular application. But people typically, for surface texture applications, just do a linear fit across the entire evaluation length. Then once they get the data leveled, they will select the roughness button, and that displays the filtered roughness and analysis settings window that we see off to the right here. And on here, the first thing a customer would want to do is determine, okay, do I want to use ISO 4287 or ASME B46.1 parameters from a calculation. So in this particular application, I've selected the ISO setting for the evaluation that we're going to do on this particular example. The next thing you want to do is select the type of filter that you want to use for your setup. So there are multiple filters that are available. There's Gaussian. RC2 is a kind of an older filter for 2D profiles. Gaussian regression, robust Gaussian regression filter. So there's a host of different filters that can be applied. And again, the key is selecting the filter that works best for your application, for your customers, for your organization, and sticking with that. Because anytime you change your filters or any parameters here, it's going to change your measurement. So you are trying to select a standard and say, this is my gold standard. I know that this is a good part. These filters selected, and then you stick with those filter selections on future measurements so that you have so that you can compare apples to apples. Otherwise, you're going to be comparing different measurements with different filters, and you're not going to be consistent. So the next thing you want to do is determine if you want to select a bandpass filter, where you use both a short cutoff and a long cutoff. Here, the short cutoff is using a 0.08 millimeter cutoff, and the long cutoff is using a 0.8 millimeter cutoff. Or you can select individually the short cutoff or the long cutoff or both. You can use standardized cutoff filters, or you can actually type in a special cutoff filter. So there are industry standards that are used that go in accordance with, like the ASME B46.1 or the ISO 4287, or you can apply specific cutoff filters that relate to your specific application. So once you select the filters that you would like to use, then you have off to the right here, you see there's a total profile, roughness profile, and waviness profile, and you can select calculations for each one of those different profiles. So here we're selecting PA, which is the total profile average roughness. Then we select RA, which is the roughness profile of the filter data, the data that's filtered by the cutoff filter. And then the waviness profile, or WA, is the data that passes through the cutoff filter. So once we select the appropriate filters that we would like to use for our measurement, the resulting display is shown here, where we have the raw data, or the primary profile, or the total profile. The waviness profile is displayed, and then the roughness profile is displayed. And in the upper right hand, you see the arrows pointing to the box. It displays the RA, the PA, and the WA. Now, even though the same calculation is used for each one of those, the filtering that's applied is slightly different so that we get different results. So you see the RA is about 1,700 nanometers, while the WA is over 7,000 nanometers. So by applying the filters and using the same calculation, we get different numbers. So this is typically how a system like the Dektak XT is used to get the information that a customer needs using a Stylus profile. And so once you collect the data, you can do a whole host of further analysis. You can do things like database analysis of the data. So here we see we did the scans 1, 2, and 3, and at the top you see we have an RA profile. We have a total PA profile, or the primary profile, and the WA for the waviness profile. And then we have the results for scans 1, 2, and 3 for each of those, and the results for each one. And then below that, we have the average and the standard deviation, the maximum, the minimum, and the range of values. And we can also display the data as a graph in here. So this gives you very, very useful information for evaluating not just a single profile, because when you're doing surface roughness analysis, you don't want to go with just one data point of a single profile across a certain section of it, because your sample, of course, can change from one region to the next. There may be defects, scratches, or other things. that you may miss by doing a single profile. So you typically want to do a number of scans across there and get an average or standard deviation. We'll look at the variation from one area of the part to another, or even looking at slightly different parts. So you can have multiple scans on the same location on multiple parts and compare one part against the other to look at the standard deviation, to look at variability of the various parts, or over an area of the parts. You can also do 3D analysis with the Stylus profile. So this is an image from the Dektak XT Stylus profiler, where we generated a three-dimensional image of a surface that has both a repeated line width on here, but then going in the other direction, there's some roughness between the profiles. So if you were to do a single scan across here in one direction versus the other direction, you're going to get very different information. So again, doing 3D mapping gives you just much more information than a single profile would. In addition to giving you pretty pictures, it gives you a lot of information. And you see this was an area that was done over a 7mm area square. And off to the right, you see the total height profile in nanometers. So it gives you much more information by doing 3D analysis. The downside of 3D analysis for the Stylus profiler is it can take much longer to collect the data. But again, you get a lot more information. And once you collect the data, then you can do individual cross-sections of the data. So here we see at the top, we're doing the cross-section laterally or horizontally across the image to the left. And in the lower right, we see a cross-section that is going vertically across the image on the left. So we're getting much different numbers for our roughness on the top value because we're going down the middle of one of those trenches, and there's some roughness in there. It's showing about 1,700 nanometers. But if we go across those multiple peaks, and the peak values are much higher, our roughness value is on the order of over 5,000 nanometers. So again, just by doing a single profile across the sample, you're going to get very different numbers depending on where the Stylus tends to land. So by doing three-dimensional analysis of a surface like this, you get much more information. And you see in the upper right-hand corner, there's an arrow pointing to a box. That is giving us the roughness value over the entire area of this scan. So you can either do profiles of just a region of the data, or you can get the calculation for RA, for RP or RQ, RT, RG across an area as opposed to just a single profile. So there's a lot of value to doing 3D analysis with a Stylus profiler, in addition to doing the 2D profile. So you can either do single profiles of multiple locations or multiple parts and compare them, or you can do 3D analysis by doing multiple scans. Now, the way that Stylus profiler does 3D analysis by rastering multiple scans across the surface. What you have to keep in mind is that the distance between each one of those profiles or each one of those scans can vary. So you need to keep in mind that by having those profiles too far apart laterally can actually act as a filter as well. So when you're collecting data, you can get a lot of information and generate some very beautiful images. But your profile density, or the distance between each one of those profiles, really can affect the measurements and actually act as a filter of the data. So we're not only talking about filtering the data by applying cutoff filters, but the actual measurements themselves can act as a filter, or the methodology used can act as a filter. So again, it depends on the spacing between each individual profile. And in the case of the Dektak XT, the minimum spacing between each profile is 1 micron. Now you can generate a 3D map anywhere from 10 profiles to 10,000 profiles, but you have to keep in mind that a very high resolution 3D map over a large area can take a lot of time to complete. So a lot of times there's a trade-off you have to do with regards to the size of the area you want to map versus the amount of time that you want to spend collecting data versus the resolution that you're trying to achieve, or the trying to minimize the filtering of the data by having spacing between each profile be too large. Another thing that can act as a filter is the actual size and shape of the stylus. Here on the left, we see a 2-micron radius tip with a 60-degree cone angle. And on the right, we see a image of a larger radius tip, 12.5 radius tip. So the smaller radius tip, the 2-micron radius tip, is specified typically for surface texture measurement. So both ISO and ASME specify a 2-micron radius tip. That way, everybody's using the same size radius tip when they apply these filters to the data. However, ISO typically recommends a 60-degree cone angle. I'm sorry, ASME recommends a 60-degree cone angle, while ISO, you need a 45-degree cone angle to be compliant with the ISO specifications. But keep in mind, by using a larger tip, the tip itself can act as a filter. So you see at the tip here, it's not getting all the way to the bottom of these V grooves, and the resulting profile shown at the bottom using the larger tip looks more like a wave, and it doesn't get down as deep into these grooves as a smaller radius tip. So again, you have to keep in mind that the tip is a limiting factor for the Stylus profiler. And optical profilers such as the Bruker Contour GT systems actually have a filter in their software to correlate the Stylus profiler with the optical profiler data. So that information is important to know. The size of the radius of the tip is important to know for the data that you're collecting. Another area that people need to consider is the data point density, because again, the number of data points used can act as a filter of the data. So here we see the red dots are the data points that are distributed across this particular scan, and you see the peaks and valleys. It's basically missing many of the peaks and valleys. So the resulting profile will look kind of smooth compared to the peaks and valleys that we see here. So having too few data points can actually act as a filter of your measurements. So again, in the case of the Dektak XT in our example here today, the Dektak XT from Bruker offers up to 120,000 data points per scan. So it gives you excellent data point density for multiple applications. And again, the maximum data point density on the Dektak XT is 0.003 microns per data point. So this, again, is something you really need to consider when you are doing your measurements so that you have the correct data point density for your particular scan, because, again, all these things can act as filters: the stylus size, the number of profiles, and even the number of data points per scan. One of the last things that you really need to consider is the noise or vibration. And noise can also act as a filter, or if you don't do something to filter out the noise really limits your resolution. So noise is what we call a resolution killer. And if you're trying to achieve the best resolution for your particular measurement, you need to do everything possible to eliminate noise. So again, in our example here, looking at the Dektak XT profiler from Bruker, several steps were taken to eliminate noise from the measurements. And this is similar with almost every metrology tool. You need to take these steps to eliminate noise. So the first thing you need is a stable platform. And again, in the case of the Dektak XT, and the image in the upper right-hand corner, you see there's a beam design on the Stylus profiler. So the sensor head is supported with this very rigid, solid aluminum structure that supports the sensor head. So that gives you a very stable support mechanism for the sensor head, which you need to do that. If you have a cantilevered arm that's hanging out over a long area and there's vibration, that cantilever actually acts as a diving board and actually exacerbates the noise. So you need a very stable platform to support your sensor head for your measurements. The next thing you need to do is vibration isolation. You need some way of filtering out or eliminating the noise or floor vibration that can be prevalent in almost any environment. So if you're talking about a machine shop where you have multiple polishers going on, or even things like vacuum pumps that are pumping, and there's multiple sources of vibration in almost every factory situation. So you need to make sure that this metrology tool, this measurement system that you're using is well isolated. So there's vibration isolation cables you can purchase from companies like TNC or Newport. In the case of the Dektak XT again, we actually have vibration isolation feet that are built into the Stylus profiler so that these are pneumatic isolators that are inflated using some sort of air supply. But you have to, this is very important, have some way of isolating your metrology tool from external vibration. The other thing, there's an internal source of vibration that comes from electronics or even the motors in the mechanical profiler that are scanning the stylus or the sample during the scan. So you need to have a way of shielding the electronics from the actual measurement source. Now, in the case of the Dektak XT, we use an LVDT sensor, a linear variable differential transformer, which detects the vertical motion of the stylus. And by removing the effects of the electronics from that sensor head, you get much more stable, more repeatable measurements. So again, you need to shield the measurement data from the effects of mechanical noise and electronic noise as well. And finally, one of the last things is using some sort of environmental enclosure. This reduces the effect of acoustic noise, such as loud, in many cases you have loud fans that are blowing or air conditioners. So even just the air blowing across the stylus tip itself, and again, these stylus systems are very, very sensitive tools. Some of them can measure down to the nanometer scale, and just the air blowing across the tip or acoustic noise from loud noises in the factory can affect the measurement and, in effect, filter your data. So you need to eliminate the environmental noises or effects from your measurements. So having some sort of enclosure, and you see in the lower left of the screen here the image of the Dektak XT with an enclosure with a door that opens and closes to minimize the effects of environmental noise. So all these improvements or all these steps that are taken really gives you the ability to get the best measurement repeatability possible. And in the case, again, of the Dektak XT in our example here from Bruker, we get better than 5 angstroms 1 sigma repeatability of our measurements for, this is using a calibration standard from VLSA, a 1,000 angstrom calibration standard, measure the step height of that standard. So the Dektak XT achieves very, very good repeatability of its measurements. And again, that's the main thing you want from a stylus profiler is measurement repeatability, because you take all these efforts to standardize your filtering and all these efforts to use the same type of ISO or ASME filtering for your measurements, but if your stylus profiler is getting different measurements from one day to the next because it's got a variability in noise or vibration or just the measurements itself, then you're not going to be able to standardize your measurement. And so it doesn't really matter which standards you pick if you don't have a repeatable measurement tool. So it's really important that you select a measurement tool that's going to work best for your particular application. So Bruker actually offers multiple types of measurement systems for different applications. On the left, you see an atomic force microscope or an AFM. The AFMs provide the highest resolution possible, both in Z and in X and Y, and multiple modes for multiple applications. So Bruker has the new fast scan icon AFM that I'm showing here on the left. This gives very, very good resolution, and it gives you the ability to get very highly accurate measurements of surface texture down to the nanometer scale. So nothing is more accurate. But the limitation of the atomic force microscope is it doesn't let you have very much Z range and doesn't give you a very large XY range. So you typically can't measure an area more than 100 microns by 100 microns. It's over 10 microns high. So although this gives you very, very high resolution, you have to limit your Z and your X and Y range for your measurement. Optical profilers that the Bruker also offers, and here in the middle, this is the Contour GT optical profiler, it's a tabletop model. This gives you very, very good Z resolution. It's a non-contact method, and many people prefer non-contact these days. They're afraid of touching the surface. But in the case of the AFMs, it's scanning across the surface at very, very low force, so it's not going to scratch the sample. In fact, it can even look at surfaces that are fluid or polymer surfaces. Optical profilers, again, the non-contact method, so there's never an issue with scratching the surface or anything like that, or having to be concerned with that. But it doesn't give you the same resolution as the AFM. The big advantage of the optical profilers is speed. It gives you very, very fast 3D images that you can collect very quickly, and you can even stitch together multiple images to look at a very large area. So with the optical microscope, you may have a very high magnification objective that only looks at a very small area, but if you want the highest resolution, you can stitch together multiple images and create one large 3D map. And again, the Stylus profiler that we discussed earlier, the Dektak XT, is shown on the right. This gives you the ability to collect very repeatable measurements and 2D profiles very quickly. It does give you the ability to collect 3D images as well, and it uses the same software as the optical profiler, the Vision 64 software. It's a Bruker software that I was showing you earlier, and that gives you very, very nice 3D images and 2D analysis of the data. So again, you may be wondering, well, which is best for my particular application? Well, in Bruker's case, we offer multiple different metrology methods, and it's often not really easy for us to give you a simple answer, which is best for your application, without actually doing some evaluation. So typically at Bruker, what we will do is have customers send samples in. We look at the various samples and determine which metrology method works best for that particular application. So that's what I would encourage you to do before you go out and purchase a metrology tool, evaluate the system, do measurements on multiple different types of tools, and determine what works best for your particular application. So finally, I just wanted to point out that there is a very nice application note on the Bruker website. It's titled ISO Standardized Filtering for Dektak XT Stylus Profiler. So this presentation that I gave today was based on the information in this application note. So please go to the Bruker website and get that information if you would like to find out more about what was discussed in the presentation today. This application, of course, provides much more detail on the various ISO and ASME parameters, such as RA, RQ, RT, and how those are calculated in both ISO and ASME. You can, again, get that information on the Bruker website, www.bruker.com. And so please go to the Bruker website, click on the Stylus profiler in the products, and or go to the application link in there, and you can download this application note right from the website. There's also a good book called ISO Geometrical Tolerancing Reference Guide by Alex. I'm probably going to mess up his name, but it's Krulowski. And he compares and contrasts the ISO and ASME standards. So if you'd like more information, you can go on the web and find out more information in the book. You can also get the ISO 4287 standard, the ISO 4288, and the ASME B46.1. All these standards provide much more information on the various types of applications that you may need. So, my conclusion here is just, to determine what is best for your particular customers, for your application, for your particular market, or for your organization. You really need to do some research. So please go out and get the information you need. And with that, speaking of research, I'm going to allow you to ask some questions. And I believe we have some questions that were asked on online here. Sarah, did you have some of those questions that were asked by some of the attendees?
Yes, Tim, thank you. Let's start with there are a couple of categories, I would say, of questions. The first related to RA versus SA. If you go to slide 27, the question is the RA on slide 27 the same as SA?
That's a great question. The SA is a parameter that is just recently becoming more and more popular. In the past, everyone focused primarily just on RA because they were using 2D profilers. Now, with the advent of 3D measurements, more and more people are wanting to look at RA over an area as opposed to just a single profile. So RA is calculation that's derived by just looking at single profile. So when the RA that was shown in that slide was just looking at the profile in one direction and getting an average over all those profiles. Now SA is a new parameter that's looking at the area over a surface area as opposed to just a profile. And so with the, as I mentioned, you have optical profilers can generate very fast 3D images. SA is becoming much more prevalent and popular. And more people are wanting to get more information about their particular process or the surfaces that they're looking at and evaluating. So again, you know, a lot of companies have standardized on RA, so they've used it for years, and they're going to continue to use it because that's what the process is built around. But now, with surfaces becoming much more complex and the tolerance is becoming tighter and tighter, more and more organizations are looking at SA, look at surface roughness over an area as opposed to just the individual profiles. And I hope that answers your question. If you'd like more information about the SA versus RA, that's a great topic, and maybe that would be a something that Bruker could look into in the future. That's a whole other topic that can take quite a long time to explain.
Tim, following along that same line, there's a question regarding the correlation of RA to SA. How is that done?
Again, there's a lot of difficulty when you're talking about correlation. So, you know, when I talked earlier about just doing a single 2D profile versus a 3D area profile, that's very, very difficult to correlate because depending on where you do your 2D profile, you can get very, very different measurement results. So your RA, as I showed in that 3D map example, by doing your profile in one direction versus the other direction, you're going to get very different numbers. So correlation is probably the most difficult question that we get because people want to correlate optical profilers versus Stylus profilers or AFM versus optical profilers. And when you're looking at different techniques and different filters and how those are applied, it's very, very difficult to do. But again, by applying the correct filters, you can correlate measurements from one measurement technique to the next. And by applying the appropriate filters, you can correlate SA versus RA. So the filtering really is important. And again, the big thing that I can't stress enough is that you have to be consistent in your filtering. I think you find filters that work, whether it's Gaussian or Gaussian regression or our filter, you know, you need to find the filters that work best for your application and stick with them because anytime you change those filters, you're going to get different results. So I think selecting filters that work for your particular application is something that only you can determine. You know, we can provide some advice and give some experience and what has been done by other companies or other organizations or other customers or another application. But it's really up to you to determine what works best and stick with it because, again, anytime you change the filtering, it's going to change the measurement you collect.
Okay. Here are a couple of questions now kind of revolving around the stylus themselves, the styli.
Mm-hmm.
So how does Bruker calibrate the stylus radius, and what is the standard deviation of the stylus radius?
So that is another good question, and there are different styli course, and different manufacturers of the different stylus. Now, in many cases, we will use an SEM to verify the radius of the tip and the cone angle of the tip. So the tips can be manufactured in a variety of different methods. They can use it. All the tips are diamond, but in some cases you may use a traditional diamond lathe to shape a conical shape to the tip. And the diamond lathe doesn't give you as much control as some other methods. So typically, if your tip is 2 microns or greater in radius, a diamond lathe is typically used. But if someone wants a smaller radius tip, in some cases we have tips that are 200 nanometer radius or even 50 nanometer radius, the only way we've found to achieve that type of radius is by using a focus ion beam or a fib, which enables you to get down to very, very tight tolerances. And again, the larger tip radius, your tolerance may be plus or minus half a micron. But on the smaller tips where your radius is 50 nanometers, your tolerances may be in the order of just a few nanometers. So it really depends on what exactly it is that you need. But I think for most machine applications, the 2 micron radius is what is recommended by both ASME and ISO. And the cone angle is also something that's important to consider. As I mentioned before, ASME recommends a 60-degree inclusive cone angle to be in compliance with their B46.1 standard, and ISO recommends a 45-degree inclusive cone angle to be in compliance with the ISO specification. So it really depends, again, on what specification you're trying to comply with regards to the tip that you use and the cone angle.
So Tim,
I hope that answers your question.
Yeah, following, just maybe a follow-up question from me. But as far as calibrating the stylus radius, is that something that's done in the system for the measurements themselves, or Oh,
I see. Well, the tips themselves aren't really calibrated per se, but we do have specifications for the tip that the vendors or the manufacturer of the tip needs to comply with. So again, they use an SEM to determine the size and shape of the tip. Now, you may be talking about some cases you may need to apply tip deconvolution to remove the shape and size of the tip from the calculation. And CMMs do this all the time, where they use a resin ball at the end of the stylus or the probe. And the resin ball is a specific radius and shape. And let's say that resin ball is 25 microns radius. Well, they take the size and shape of that ball and they deconvolute that from their measurements, so that if you're looking at roundness or form, you remove the shape of the tip from the measurement. So that's important in a lot of specifically shape measurements. And the optical profilers as well, if we're trying to, I mentioned this earlier, trying to correlate the measurements of an optical profiler with a stylus profiler, you actually remove the size and shape of the tip from the optical profiler measurement so that it correlates with the stylus profiler. So again, the size and shape of the tip can act as a filter, so you need to make sure that you either use you understand the size and shape when you're doing the measurements, or you use a system that can provide deconvolution of that tip to remove that shape from your measurements.
Okay. Now there's a cluster of questions and comments regarding the standards themselves. One of the latest questions coming in: is it possible to use ISO versus ASME in Profiler on the Dektak 150?
Well, yeah, you could, because you can select both ISO or ASME. So you could do one measurement using the ISO specifications and another measurement using the ISO specifications, and compare and contrast those two measurements and see what the difference in the measurements that you're getting. So you could actually scan in the same locations, in the same stylus, with the same filter, whether it's Gaussian or Gaussian regression filter or 2RC, and just click on a button to select the ISO standard or the ASME standard and do another scan. So, and then you can compare the results right there on the screen. So it's very, very easy to do on the Stylus Profiler if you wish to do that. I'm not sure what the benefit of that would be, but you know, it can certainly be done.
Okay, then just a few comments. Sorry, just seeing another question come in. Just a few comments regarding the standards themselves and some clarification. The latest version of the B46 is noted that it's 1-2009. Tim, can you confirm that? And then also that the 90 degrees is also okay to use for B46. I believe you mentioned a 60-degree stylus tip, but someone wanted to confirm that also 90 is spec'd on the B46 standard.
Well, the specification specifically requests or recommends the 60-degree cone angle to be in compliance. So, you know, it's just they're trying to set a specification so that everybody's using the same parameters for their measurements, so that when someone in one part of the country or part of the world is using these parameters and they use the same tip, they're going to get similar measurements in another part of the world using the same parameters and the same tip. So the cone angle only comes into play if you are getting into very narrow peaks and valleys. And again, the size and shape of the tip is probably more of an issue than the cone angle, although, you know, once you get greater than 90 degrees, the cone angle becomes a very big problem. But I'm not quite sure how to answer that question because, you know, I'm just going by what the ANSI specification with the request now recommends. And I haven't specifically read anywhere in the ANSI specification that it recommends a 90-degree cone angle. It could be in there, but I just don't recall seeing that as one of the specifications. But again, the important thing is you just, if that's what you've been using in the past and you've standardized and created your gold standard for your particular parts using a 90-degree cone angle, then I would recommend sticking with that if you're going to compare past measurements to new measurements. So if you're going to start from scratch and today want to use a 60-degree cone angle, you know, you can do that. But again, using the same cone angle for your measurements, so you're comparing apples to apples, is important. Changing out the cone angle now when you standardize in a 90-degree cone angle is probably not a good idea. So I just recommend using consistency is really the key when you're talking about filtering and these measurements. So you want repeatability, repeatable stylus sizes, repeatable measurements, and repeatable filtering so that you can really compare one scan against the other and say, okay, this is a bad part and this is a good part based on the comparison from one scan to the next.
Okay, we're coming up on our hour time frame. There are a couple of other questions. Not to worry, those questions won't be lost. We will get back in touch with you to answer those that we weren't able to read aloud here.
Okay,
also
my
note,
email is also on the screen here if anyone would like to email me some questions after the presentation.
Sure thing. And then just to make sure everyone, if you would please fill out the survey. I think it's a 5-question survey as you exit. And the webinar and presentation will be available for download online. You will all receive a thank you letter with links for being able to download the materials. Tim, would you like to
thank you very much, Sarah, and thank you everyone for joining us today. And please, if you have any additional questions, you can email those to us. And I want to thank you for your time today to participate in the webinar.